So again, we're just going to do a simple simulation of Conway's Life, the game of life. You may have heard of this. It's a very famous simulation out there, but we're just going to do it. Just a note on the pesky tourist stuff. That was a challenging assignment this past week, and so if it's still pesky to you, I'm allowing students to turn it in all week this week also without any late penalties. So if you're still working or never got it or stuff like that, let us know. Keep working on it. Or else, and check with the TAs if you have questions on that also to work on that. So, but again, today we're going to do Conway's Life. So we're going to do this learning activity, and then your job is to post your kind of pattern that you create and your code for creating it through the discussion group hopefully by the end of class, but certainly by Sunday. So let's look at the learning exercise. This comes from the Think Java class or book where they talk about arrays of arrays here. They talk about Conway's Game of Life. This was one of the first simulations that were, once we got computers that were fast enough to kind of do some of this stuff. It was from 1970 when computers were just coming out here. And it was one of our first examples of dynamic systems. And dynamic systems are a special area in math and simulations where you can create very complex things with very simple rules for this. Since then, we've had a number of examples of this, but the idea is that with very simple rules, you can often generate very complex results there. There's a sub area of this called chaos theory or chaotic systems, and you can create chaotic systems also with these very simple results. And there's a lot of the complicated areas in science often are a result of chaotic systems. So if we try to understand how water flows through a busy river, how weather interacts, how turbulence works, all those are related to this chaotic systems. And again, it's hard to model. And we'll see today, just modeling a very simple system, how complicated the results can get here. So again, this textbook talks about it, introduces this sort of idea here. We have a relatively simple rules for life here. We've got cells that are either on or off here. You might say is they're either alive or dead. So the black cells here are alive and the white cells are empty or dead. So we have some active cells and inactive cells here. And then there's rules. Here's our rules. If we look at a cell that's alive or active, if it has fewer than 2 neighbors, it will die or become inactive. So like this cell right here, it only has 1 neighbor. So what are neighbors? Neighbors are the up, down, left, and right, and also the diagonals. So anything in the 8 cells that surround it. So there's only 1 that is alive. So this cell will become inactive or it will die because of loneliness or underpopulation here. If a cell has more than 3 neighbors and it's alive, it will die of overpopulation. In this example, there isn't one. This one here actually just has 3 neighbors, 1, 2, 3 here. So again, any cell that has like 2 or 3 neighbors, and it's any active cell or a live cell with 2 or 3 neighbors will stay alive. That's the right number of population nearby. Now, then also, if an empty cell is here and it has exactly 3 neighbors, it'll become active. So we'll repopulate that or generate a new cell there. So like this one here in the middle, it has too many. It has like 5 neighbors. But like this one has exactly 3. So any cell with 3 neighbors will spontaneously become alive. for that. So those are our simple rules for this. Now, the code we'll be looking at, we'll have a cell class here. We'll keep track of where in the grid we are and how big this is, and we'll draw out this grid for us. Again, we don't have to really understand how this all works. We draw out rectangles and stuff for this. But again, it just has an on or off state, a 0 or a 1 here. And then we have a two-dimensional array. And this kind of gets into this stuff where, and this is how we declare our two-dimensional array. Now, usually we've been looking at arrays of like integers or strings. We really, in this class, we don't get into creating other objects. If you go on to programming 2, you'll create other objects like this here. So we create a cell object, and then we create an array of those cell objects. So again, we'll learn again in the future that you can create an array of other objects. So that's what this is doing. So that's why it might look a little weird rather than saying like int array here. This is a cell array for this. With normal two-dimensional arrays, we have this loop. We have to loop through all the rows and loop through all the columns. And then we'll draw or create a new cell for each of these locations here. And so again, we have an array of rows, and each row is another array of columns, and that creates our two-dimensional grid for this. There's some more information about this and how we draw the grid. This isn't all that important, but here is, again, where we start. We have a code called Conway. We create a grid, and then we turn on certain cells on the grid, and then we'll run this here. So let's try this out. So again, go into Unit 11, go to the learning exercise. You can download the zip file and unzip it and open it up. So, or you can go to this GitHub area, grab that, and go to NetBeans, go to Teams, and there should be a Git here. If it's not, you're probably already clicked in a project that's already a Git project, says master here. I'm just going to click off of that project and do, now I say Teams Git clone, paste in my thing and hit finish. Oops, I've already cloned this once, so I've got to give it a slightly different name, I think, here. Okay, so here's our life game. So again, there are three different files in this thing. One is the cell file, and we kind of talked about that just now. It just defines how a cell works here. Every cell has an X and Y coordinate and a size, how big it is that we're going to draw it out on the grid. And then we keep track of it if it's on or off, active or not. We then have a grid of these where we have an a two-dimensional array of those cells here. And this is our code for setting that up. And finally, we have the Conway class. Inside that is a bunch of stuff. There are rules where we count how many neighbors are active. And then we have the rules for turning things on and off. So again, if a cell is on and the count is less than 2, it dies of underpopulation or loneliness. If it has too many neighbors, more than 3 neighbors, we turn it off because of overpopulation here. And then if a cell is off and has exactly 3 neighbors, we turn it on. So this is just our rules for the simulation. So see if you can download this example and then go through these questions, see if you can kind of understand it. And eventually we want to get down here. We want to get to our Conway Life game with some initial code here. And if we run that, It should show a simple simulation of this game, or this, not a game, this, yeah, simulation. It should show these blinking values for that. So I'll let you play with that. See if you can work through and answer. Now, there's nothing to turn in as far as these questions goes. These are just trying to get you to better understand it so that you can create interesting patterns. Okay, just a quick break in here. Once you kind of get an understanding, kind of look through these questions of how this works, you'll work mainly in this Conway method here. We want you to look at this grid canvas and play, we have the number of rows, number of columns, and the size. And again, you can play with this size and try to change it, change number of the X or the Y, the rows or columns, and see how that works. And you'll get different results. Here's with a size of 50 here. And then we'll lay out the grids. You'll turn on certain cells. I sometimes like to do this on graph paper or something like that. Here's a little spreadsheet. So I'm turning on 2, 1. So row 2, column 1 is there. And then 2, 2, row 2, column 2. 2, 3 is there. And then let's see, 1, 7 is here, 2, 7, 3, 7. So initially I'm turning on these 6 cells, and then they simulate. And again, every cell here, like this cell here, will it's active, but it'll come inactive because of loneliness. It'll only have one neighbor. This middle cell stay on because it'll have 2 neighbors. This cell here will actually turn on because it'll have exactly 3 neighbors. So your job is to set this up, figure out an interesting simulation here. This is kind of the default one with 2 blinkers like we have here. But your goal is to add in some more here. So maybe you want to add in some other cells. So again, you can look or you can just pick different ones. So maybe I want to add in another one here at 3, 3. Here, maybe I want to do a new one there. So I would say, grid dot turn on 3, 3. So I've added that. Here. And then I can run this again, see if that makes a different kind of simulation. Here. Now, on some of these, we might want to make a bigger grid. So you might want to change the size of this grid to something bigger here, so that when we run it, and then maybe make this a little smaller, you get a bigger grid and you can see how things work. So try to find a really interesting pattern here by turning on and off turning on certain cells, and see what kind of interesting patterns you can find here. So hopefully you're seeing some of the dynamic patterns that can be generated from simulation. So a lot of times simulations like this are used in a lot of dynamic systems. You can imagine we use the same sort of stuff to predict the weather, and we look every maybe hour ahead and try to predict and we have rules for predicting what the temperature, wind speed will be. And again, we break our world up into little grids like this, and we predict things one step ahead in a lot of places. There's a lot of people have worked with this Wiki Life. There's a whole area that if you scroll down to the bottom of the assignment, there's this Wiki Life thing where they have whole bunches of patterns out there that you can look at. So you can look at these patterns and they'll show these different patterns. A lot of them are repeating patterns. A lot of times people try to create repeating patterns that repeat on a certain frequency for this. And people try to find patterns that repeat on a longer frequency, these kind of oscillators that'll run. And again, our initial one, the blinkers, were a simple oscillator with just 2 they went back and forth at a cycle of 2, where this is a longer pattern, which will cycle through here. So I'd like to challenge you. I mean, it's interesting to see what patterns you can come up with. Here's one that I've accidentally stumbled on. And it's just a pattern, but it creates this little thing, which is often called a glider, which is a little pattern that moves across the screen. It replicates itself and slowly moves across the screen as it goes, here. And it'll keep going until it hits the edge of the screen. My screen isn't that big, so it'll hit the edge pretty soon. And then it'll stop here at the edge of the screen. I found an interesting pattern starting with our blinkers and just adding a couple cells, which I think runs for an incredibly long time without duplicating itself, without repeating itself. So if I run this, it'll run for a long time. So if you find a pattern that you think runs for a long time without, getting in a cycle, be interesting to compare how long they run with this one, because I think this one runs for a long time. Also, if you have a repeating pattern, it'd be interesting to see that. How long can you make a repeating pattern go? And one thing you'll see, we often call these chaotic or dynamic systems because, again, one small change in the initial condition will drastically change how this simulation will run. So the initial conditions are very important. It's very hard to predict what the system will be like in the future, in 10 spots based on initial configuration, because it's so dependent on, slight changes in the initial configuration drastically change the output here. So, okay, so keep trying to find interesting patterns. You want to post the pattern. This is still going here. So to the discussion area, you want to grab a screenshot of your pattern at some point in your pattern, grab a screenshot of, and then post the code from your Conway method so other people can duplicate your pattern and try it out. So post your code and a screenshot through the discussion once you get an interesting pattern for this. If anyone gets a pattern that they think runs a long time, we can compare it against mine and see how they run. One more thing, if you're trying to do these complicated things, you're wondering why it runs so slow. In Conway, the file, if you scroll down to the bottom, there's the main loop that loops through, updates, and repaints the screen. It sleeps for half a second. It actually slows everything down. So if you want to speed things up, you can go down to the main loop and change the sleep time, like from 500 to 100 there. And then if you run this, it'll run a lot faster for this. So if you want your simulations to run a lot faster, go down to the main loop of Conway and change the sleep time from 500 to 100. And then your simulation will run very fast.